All right, so we're also going to study what's called the ratio test, which is another series convergence or divergence test. However, the ratio test is going to help us determine whether a series is absolutely convergent or if that series is actually divergent. So it's not going to tell us anything about conditional convergence, and we're going to see why in a second. We're only going to consider series that have functional forms of its a sub n function that are either factorials, numbers being raised to powers of n, or n to the n type terms. So what I mean by that is we could have terms that are like, say, n factorial, or maybe like, say, 2n factorial, things like that. So if a series has those types of functions in it, we get to use the ratio test. Or if we have numbers being raised to powers of n, so if we see things like, for example, I don't know, 2.5 raised to the power of n, we could use the ratio test. Or if we see n to the n type terms, quite frankly, literally meaning n to the n raised to the power of n. If our series function a sub n has any of those types of things in it, we can probably use ratio test. And well, what ratio test actually tells us is the following. We really consider then another limit. So we take the limit of our series function, a sub n, but we take the next general term in the series. So we take the ratio of the n plus first term in the series, and we divide that by the nth term in the series, and we take that limit in absolute values. And depending on what this limit turns out to be, tells us whether or not our series is absolutely convergent or divergent. So let's take a look at what can happen with this limit. So there's three possible things that could happen when we take this limit. The first thing is if this limit is any number less than 1, as in it's going to be some number between 0 and 1, then this series is convergent, but not only convergent, it's absolutely convergent. If this number is anything greater than 1, coming from this limit, then our series is just divergent. And the third case, if this limit turns out to be exactly 1, it's inconclusive. And well, that inconclusive really means what's happening is we're likely applying the ratio test to a series we shouldn't be. In other words, we're applying the ratio test to a series that maybe it doesn't have any factorials, numbers raised to the power of n, or n to the n type terms. So we're applying the ratio test to a series which we shouldn't be applying the ratio test. So we probably should look for an alternative series convergence or divergence test to help us out. So that's really what the ratio test is. We are considering the limit of the ratio of the n plus first term to the nth term in the series as n goes to infinity, all in absolute values. So let's do an example of this. So in this case, let's consider the series from n equals 1 to infinity of, let's do, say, a minus 1 to the n times an n squared all over 4 to the n. And now, again, we're going to try and apply ratio test, but in order to use ratio test, we need to make sure that one of those three functional forms are there, either factorials, numbers raised to powers of n, or n to the n type terms. And what we see in this case down below is, well, we see that number 4 being raised to the power of n. So because we have that 4 raised to the power of n, it looks like the ratio test can be applied in this case. So let's apply ratio test. We look at the ratio of the n plus first term versus the nth term. So let's just practice writing out what the n plus first term is. So the general n plus first term in the series is going to be, well, anywhere we see an n in the series function, we basically just replace that with an n plus 1. So our n plus first term would be a negative 1 to the n plus first. And then we have n plus 1 quantity squared all over 4 raised to the n plus first. And that's in comparison to just the general nth term, which for us would just be exactly what's inside of that series, -1 to the n times n squared all over 4 to the n. So let's look at the ratio of those two things and take the limit as n goes to infinity in absolute values. So the limit as n goes to infinity in absolute values of the n plus first term, so maybe we should just write that out, n plus first divided by a sub n equals the limit n goes to infinity in absolute values of the n plus first term, so -1 to the n plus 1 times n plus 1 squared all over 4 to the n plus 1, all divided by, well, the nth term of the series, which in this case, the nth term is just, well, the term that's sitting there kind of inside of our original series, a -1 to the n over n squared all over 4 to the n. So we're taking the ratio now of a lot of fractional-like things. We have a fraction sitting on another fraction. So let's make sure that we can remember what we do in this case when we're taking a ratio of two fractions. We will reciprocate that denominator and multiply it on. So I'm just going to go ahead and do that before I cancel out any terms here. So that first fraction in the numerator just stays the same. So this would be a -1 to the n plus first, n plus 1 squared all over 4 to the n. But then we reciprocate that denominator. So this entire fraction in the denominator, we will reciprocate. And basically what that will give us then is, oops, I need a 4 to the n plus first sitting downstairs there. And reciprocating that, we will get a 4 to the n all over -1 to the n times n squared. And now we can start multiplying things, maybe dividing things out and stuff like that. But what I like to do in these types of problems is basically put all the similar functions all over each other. So what I mean by that is, well, I'll take that -1 to the n plus first in the numerator, put it over that -1 to the n from that denominator. I'll take the n plus 1 squared and put it over the n squared term. And I'll also put the 4 to the n term on top of the 4 to the n plus first. Just so when we start canceling things out, the algebra works out a little easier, or maybe I'm just less prone to make mistakes. So for example, we can start canceling things out. So we can cancel out a factor of 4 to the n out of both of those terms. However, in the denominator, we're still going to get a factor of 4 to the first left because we had that 4 to the n plus first. Now, the other thing for us to recognize, we could do the same thing with those minus signs as well. So we'll have an extra -1 sitting there in the numerator. But because we have those absolute values sitting there, the absolute values are going to squash any of those negative signs at the end of the day. So really, we could get rid of that -1 because of those absolute values. So I'm just going to rewrite this then as what we have left so far. So we're really looking at, if we take that 4 out of that 4 in the denominator, just write that as 1/4 in front, we're getting rid of that minus sign. And now we have that n plus 2 quantity squared all over n squared. And we're basically asking in this case, what is going to happen in the limit as n goes to infinity? So let's see what happens really. Well, as n goes to infinity, this 1/4, that's just going to stay 1/4. All of the n dependence, of course, is on this kind of second fraction, n plus 1 squared over n squared. And what we see is, well, as n goes to infinity, that term in the numerator goes to infinity, that term in the denominator also goes to infinity. So what we can do is actually go ahead and take Hopital's rule. Also, I can get rid of the absolute values because we're only dealing with positive things left because we've squashed basically that minus sign since we're only considering positive things at this point. So doing L'Hopital's in the numerator, we're really going to take the derivative of m plus 1 squared, or m plus 1 quantity squared with respect to n, which means taking that derivative, we'll get 2 times m plus 1 times the derivative of what's inside that m plus 1, which is just 1, all over the derivative of the denominator, which is a 2n. And then we just keep going with this limit. Taking the limit again, well, I guess the first thing we could do is cancel out those factors of 2. And we can reassess what that limit is looking like. So we have the limit as n goes to infinity of 1/4, all times, well, m plus 1 all over n. And while seeing this again, basically what we have is that m plus 1 goes towards infinity, this n goes towards infinity, so you guessed it, we get to do L'Hopital's again in this problem. So finally, doing the derivative of the numerator and denominator separately. The derivative of the numerator is a 1, derivative of the denominator is a 1. So we just finally get the limit as n goes to infinity of 1/4 times 1. And maybe I'll just write in, again, we did L'Hopital's rule a few times here. So this overall limit as n goes to infinity is just equal to 1/4. Now let's see what that means again. Depending on what this limit is, tells us what happens with ratio test. So if we go back to the original ratio test we wrote down a few minutes ago, what we saw was, well, in the case where that limit comes out to be something less than 1, our series is absolutely convergent in this case. So if we go back down, this 1/4, we saw that's less than 1. So the series is absolutely convergent. Remember, this was the original series that we started with in this case, -1 to infinity of -1 to the n of n squared all over 4 to the n. This series is absolutely convergent. And what that means more in a practical sense is if we got rid of all those minus signs, that series would still converge if we're only looking at kind of the only positive term counterpart of that series. And what that means for us is if we have that positive only term series converging, we could sprinkle in as many negative signs as we want, and that resulting series would still converge.